Well, hello friends. Welcome back to the program. Today we're going to keep working on our JavaScript JIT, and I'd like to take a look at the Octane benchmark because previously we've been focusing on Kraken subtests, and the reason for that is pretty simple. So we have these 4 JS benchmarks here in our JS benchmarks testing repository, and SunSpider is the oldest, and also it runs really fast, so it's kind of not very interesting to target because we can already run all them tests so fast. But Kraken, we take a couple of seconds for each test, so it's kind of fun to target with optimizations because it's, you have a quick edit, compile, test cycle time. Octane, on the other hand, and Jetstream even more, they are newer and slower. Jetstream is very, very slow in libjs. Octane, it's pretty bad too. In fact, let me compare 2 runs that I did earlier today. So let's see, constant pointers, that's landed in master now. So if we look here, these are on the right side, these are the current numbers on my machine. And we can see that many of the subtests, they do run in a couple of seconds now. So 4, 2, 7, 3 seconds, that's pretty good. 37 seconds, that's a long time to wait for a test. 78, painful. 27, pretty bad. 70 seconds. And 155 is particularly unpleasant. So zlib.js is the most painful test in Octane. It makes it so that I don't even want to run Octane on this machine because I don't want to sit and wait for zlib to run multiple times, each run taking over 2.5 minutes. But the good news is that it's already been improving because it used to take over 300 seconds, but with the recent improvements, with adding a JIT and then improving the JIT, we keep getting faster and faster. So it's almost 2x where we were just a month ago, but we obviously need to get it to go faster. So I think today I would like to grab a profile of this test, and then we'll just pick something in there to make faster because there's going to be a million things. And I'm going to use perf to grab the profile actually because call grind will just take forever to profile a test like this. So if we use perf, we can get a less precise profile, but it will be a more honest profile because it will profile it running natively on the CPU. So pros and cons. What am I trying to do? JS zlib. Octane zlib JS. Yeah, I'm gonna record a trace of that, although let's also grab one of with Valgrind, just so we can look around a little bit. Because yeah, the tools for perf, I feel like they're so weak compared to kcachegrind, which just has this super sweet spot of discoverability, and even though the data is less than precise in terms of, well, Valgrind runs the code emulated, so it's less like a real CPU, but it is so nice to be able to browse around and see every single call to every function. But we can have both. Although I'm not going to sit here and wait for this thing to actually run because it will probably take many, many minutes, if not an hour. So we're just going to let it run for a little bit. So we'll capture the start of the benchmark at least. Let's see how much time we've spent. We got about a minute of call grind tracing here, and this guy's probably going to go for 2.5 at least minutes. So yeah, cut him off here after a minute. And then we'll just take a look. So now keep in mind, this is just capturing like the start of the benchmark, and I don't know how far into it we got, but even so, we can see that we got millions of calls to various things. So there's a high likelihood that making these things faster will still make the whole thing faster. So what do we got? We are running in the JIT. Sure. So we got generated code here that it doesn't know what the symbols are. Makes sense. We made that code at runtime. And then we have put by value. So we're calling out from JIT code to C++ to put by value, which is when we do a like object foo is something. So this operation here is a put by value. We call it put by value because we don't know at parse time what property you're accessing. So if you were to do this, then you have an identifier. So you know at parse time what this identifier is. So we call that a put by ID, but this is put by value because this can be computed at runtime. Anyway, that is our heaviest operation with 18%. Put by value, sure. Get by value at 17%. Okay. Looks like a fair amount of typed array access. It's probably something that we could make faster. And we get variable. 14% of get variable. That one is pretty interesting. So that's accessing an environment variable that has been captured by nested functions. So otherwise, if a variable is local and not captured by nested functions, and also there is no eval, like no call to the eval function nearby in the same scope, then we turn those into what we call locals. But because somebody's capturing this guy, or because of eval, we have to use get variable. So that one might be interesting actually to do a fast path for. Put by property key is part of put by value. Yeah, you can see that it's called by put by value here. And we got right shift and left shift. Those should be pretty straightforward to just do machine code fast paths for those two operations, assuming they are in 32 values. Because yeah, that should be pretty straightforward. Can probably save a whole bunch of time there. But I feel like we've been doing videos about fast paths for these kind of things already. But we haven't done, like this one is a little bit more complicated, get variable. So maybe we should get into that one. Okay, so now we have a capture here of the full run of the thing. So let me actually I have a hotspot downloaded, which is a program that lets you visualize perf traces. And it's far from perfect. I wish we had instruments from macOS, but we don't. So as far as I know, hotspot is the best thing available on Linux, at least for browsing perf traces. I've tried all the different tools I could find. I've tried, and at least in my experience, hotspot is the nicest. I don't know what's causing this whining here, but we'll see. So we'll let that load, and we'll see if what we see in here matches the partial profile we did with call grind. So let's see if we just do a bottoms up look, sorted by cycles inclusive. And then they truncate the names in hotspot kind of interestingly, but it ends up kind of working. Like they strip out all the namespaces and stuff, which I would probably prefer to see, but fine, whatever. So we can see get by value, get variable. Let's see, I don't see put by value anywhere near here. Put by. Okay, is that how that works? I don't know. Maybe you can't search. Maybe it got swallowed up somehow. I don't know. Put by. Oh wait, it's right there. Okay, so maybe put by value is heavy at the start of the program, so we captured a lot of that in our call grind trace. But like maybe they build up this big thing at first, and then they do a bunch of read access. So maybe like the put access is front loaded or whatever. I'm not sure, but. Or maybe there's just less of it and more gets in the end. But we can still see that get variable is near the top. get by value. Get by value is going to be hard to optimize. We have to do a whole bunch of things for that, but it can be done, of course. We can make it lots faster, but it's going to be a little tricky because objects can be shaped in a lot of different ways and properties can work. There's like a whole different set of property name types that we have to deal with, and underlying object types and so on. Left shift and right shift, yeah, those can totally go faster. But get variable, I am interested in this guy. Yeah, let's see. Okay, so let me show you exactly what creates a get variable bytecode instruction so that we know what we're dealing with. Make a little test for this. So let's say that you had a function outer, and then in here you have a variable. Let's call it limit, and we'll set the limit to 100 million. And then you have a function inner, which uses the limit variable like this. Because this is captured here by the inner function, the variable limit is not within inner's own variable environment scope, but it's in one of its outer scopes, and it's in the immediate outer scope. That can't just be a simple local, because manipulating limit from here has to be visible when you return to outer. So if I were to call inner here, and if I were to manipulate limit inside inner, it has to be reflected once I return from inner. But if you're familiar with JavaScript, you know all this stuff. The interesting part is how we deal with this in our implementation. So what ends up happening, let me show you, is let's say we have a loop that does nothing. Actually, it's kind of nice because that's where we started with the JIT series, just loops that do nothing. And then we'll do increasingly convoluted ways of looping to do nothing. So if we call outer now, and let us dump the bytecode for this stuff, so we'll see that the inner program has a couple of basic blocks, but in the main loop increment area here, or loop condition area, we can see that it's checking if local variable 0 is less than a get variable 1. So that's the limit variable. So here is our get variable. And if limit were to live inside of inner as well, then that would just become a local. So if I just move it in there, we'll see how it changes the program. So now we have two locals. We have local 0, that's I would think, and local 1, or no, local 0 is, well, whichever one it is. Let me not get confused. I think probably it's still I, because local indexes are not necessarily in order of appearance for some reason. I think that's just because we're using non-ordered hash map when we assign the indexes. This has confused me in the past, I remember. Anyway, we can see that it's just using two locals, which is going to be faster. So if we compare, I guess, if we run get variable with the JIT, so we time that. So when we're using a local for both, it is about 350 milliseconds. But if we switch it so that it's in the outer scope, we have to do a get variable to traverse our scope chain or environment ancestry chain. We go from 350 milliseconds to 1.2 seconds. So it's a lot slower. And of course, a big part of that is that we've already optimized local access in the JIT. So when you're accessing a local variable in JIT code, we just fetch it from the locals array very, very fast. Here, we have to call out to C++. Where can we look at that? Get variable. So it ends up calling this guy, this helper, get variable, which does a bunch of stuff. And the most interesting of which is the fact that it has a cache, but if it's uncached, so first time we ever execute a get variable, we go straight down here. So we have to do a binding resolution on the name, which means that we look up, in our case, we'll look up the name limit within the current environment here. And when I say environment, you can think scope. Environment is the name that JavaScript spec uses. So I'm looking for limit in the current environment. I don't find it in this environment. So I will have to go into the outer environment, and here we find limit. And then we can return the value of that binding. But this cache thing is very interesting because once you have performed this lookup once, then you can remember how many hops you had to make. So like how many outer environments did you have to jump through before you found it? Because normally that doesn't change. The only way for that to change is if somebody does an eval and then screws up your environment chain. And I think we checked for that here. Yeah. So if you use eval, then we will mark the environment as like screwed up, or we call it permanently screwed by eval, which means that, okay, eval, somebody ran eval here. They may have meddled with the environment chain. We don't know anything anymore, so we can't cache these hop counts. And so, but in the common case, nobody does eval. So that allows us to remember how many hops we had to make to find limit. And then on subsequent accesses of the same variable, so like every time we go around in the loop, we check if I is less than limit. We don't have to look for limit anymore because we know it is one hop above in the environment chain. And that is what this code here does. So if cache has value, then what we do is we want to jump that many hops up in the environment chain. So you can see we just get the current running execution context lexical environment, and then we hops number of times by just like going to the environment's outer environment and then repeating that operation. And then we see where we end up. And if we end up in an environment that isn't screwed by eval, then we will return the value directly from that environment. And in fact, we don't just remember the number of hops, but we also remember the index. So an environment coordinate, that's what we call this cache. So it has a number of hops and it has an index. And the index is, it's an index into the environment where that binding lives. It's an index into its internal array of binding values, basically. So that means that this lookup, when cached, becomes a loop to jump environments and then indexing it into an array, essentially. Now, all of that to say, and that is a lot faster, by the way, than doing the lookup, because you don't have to do any string compares and you can avoid a bunch of generic stuff. So it's a lot faster. And all of this to say, I bet you we can do this in a JIT fastpath and it will be even faster. Just checking my phone here. All right, everything's good. Nothing urgent? Cool. Right, so I think we can make a JIT fastpath that does this. It's definitely going to be more complicated than the fastpaths we have done thus far, but it would be really cool to stay in machine code. So then, like the first time you access limit here, we would have to bounce out to C++. We'll do the lookup, but then we'll store the cache, the cached location where we found it, the environment coordinate. And then on subsequent accesses of limit, we can just stay in machine code, and we don't call out to C++. And then this program won't have to call out to C++ at all. And I think, like, in the vast majority of programs, get variable accesses are cached. We can verify that here for the zlib if we just do something like, let's say here's a successful one, right? So static int hit miss. Just do something quick here. Hit miss. So something like this and something like that. So just out of curiosity, like how many hits and misses are we looking at on the zlib test? Okay, so we had a couple of misses early on, but then after a while, it's just all hits, as you can see, or almost all hits. This is great. This means that if we can handle a hit path in machine code, that allows us to stay in machine code for way longer. I think that will help substantially. So great. Let's get rid of that gunk and see how we transform this here into a JIT fastpath in the compiler. So compile get variable. All right, so this is going to be a little bit complicated. We'll see. We'll just get started. So first thing I'm going to do is I'm going to just create an if zero block here with the get variable fastpath. And this is not permanent. It's just for me to be able to reference it quickly. So I think maybe the simplified fastpath, we can get rid of these verifies because it's kind of gratuitous and we already know that they should be good. And then we have to do this where we fetch the environment, which is the running execution context lexical environment. We have to do the hops. But yeah, okay, so we know, okay, first thing we have to do is we have to check if we have a cached value, sure. And then we have to get the current lexical environment, then we have to jump hops number of steps in the environment chain. Then we have to check the permanently screwed flag, and then finally we have to get the binding value from the environment that we just found. Okay. Sure. Checking in strict mode. What does in strict mode do, I wonder? Get binding value direct. It is ignored. Say what? Oh, no. Wait. What? No, it is ignored. What the heck? Get binding value direct. Wait, so nobody cares about this? And why are we even calculating it? Okay, well, that's good. That means that it doesn't matter. We don't have to figure out how to fetch that flag. Okay, so let's see. So the first thing we want to do is figure out if the cache has a value. Right, and the cache is going to be this thing right here. So this is what we're passing to the C++ helper. This is our C++ helper. So this is where we don't want to end up. This is the slow path. So, but we want to end up there the first time when it's uncached. The cache is one of these things. So it's just an optional environment coordinate. So we need to look if the optional has a value. That's the first thing we want to do. So I think we have arg2 here contains the the address of the cache. So maybe we'll just put this first, and then let's see. If cache has value, right? So we need to load. We need to load the has value flag from an optional, which means, wait, no, how do I get there? Optional. Take me to the right optional. Here we go. M has value. Okay. So it is here, and it will be at a different offset depending on the size of the T that is stored inside the optional. So I think I'm gonna need a helper for this, like a helper that can tell you where that thing is. So make something like a static flat putter has value offset. Essentially, yeah, that's basically what we want. And then we also want like value offset for the value, which is called storage internally, but the API is calling it value. So I think that's okay to call it value here. Although that's always going to be a 0, but that's fine. That's fine. If it were to move at some point in the future, it's nice to have helpers to tell you where they are in the class. Okay, so how do we load the has value flag? Let's load it into GPR 0. So assembler mov assembler operand register GPR 0. It's going to load from memory from arg2 as the base, and then arg2 currently points at the cache. So then we're going to say like optional, or no, what was it called? Bytecode environment variable cache has value offset. Okay, wait, is that right? Just need another one of those. Okay, so GPR 0 is now the has value flag, which is Boolean. So it's an 8-bit quantity. I kind of want to have like a mov 8 for this almost, where I only get 8 bits. Because these are getting 64 bits. And I don't want to load 64 bits here. I want to load 8 bits. So let's invent that for ourselves. Let's say void mov 8. And I mean, it can be pretty simple. It's offering me a whole enchilada here of alternatives. I don't know if these are accurate. Let's see. Reg to register memory destination 88. Okay, I'm just going to take these, accept these without investigating too much, and we'll see in the disassembly if it's wrong. Let's see, mov 8. So that means I would load into the bottom 8 bits. Although, is that what I want to do? I also want to 0 extend, actually. Wait, so what I really want to do is an 8. Let me make sure that I'm getting the right thing here. So let's write a little test program. So like mov rax byte from like rbx plus hex 18 or whatever. I don't know. That's not a thing. Okay, can I load into EAX? Well, I can surely do that. But if I do that, I'm not going to 0 extend. So if I, okay, there's might be a better way to do this. But I'm gonna 0 extend afterwards then. So like load the 8 and then 0 extend. Okay, maybe I'm overthinking this. There's a better way to do this, but let's not get bogged down with that right now. Instead, let's let's do this. Let's just and then we'll leave this as an optimization opportunity. So we can definitely do a better instruction sequence here. This is silly, but I just want to move forward without fidgeting with the instruction encodings right now. So we'll do this. Okay, so we've anded off. So we just have the bottom byte. Okay, great. Whatever. Now we can check if jump if we want to check GPR 0 if it is not equal to, if it is equal to 0, that means that we don't have it cached. So then we want to jump to the slow case. And our slow case assembler label slow case. And then the slow case will be down here. So the slow case is just us calling the C++ helper. That will be great, I think. Right. Slow case, call C++ helper. Uncached access, call C++ helper. Yeah. Okay, so go to slow case. Great. I'm gonna say fix me. Figure out a nicer way to load a single byte. Yeah. Okay, so now we've jumped, we are still here. This means that we have a cached thing. We may still fail the cached access if we were screwed by eval. So we're not home free yet. But the first thing we got to do is we got to figure out what is our current lexical environment. And we get that by calling VM running execution context lexical environment. So let's go to this guy. Okay, so what do we need to do? We need to get the execution context stack and then get the last entry of that stack. So that's a vector. Okay, so to get the last entry in a vector, that means that I have to get the size of the vector, subtract 1, and then multiply by the size of the t, and then go that many, access that many bytes into the underlying data of the vector. That's a lot of code that don't really feel like writing all that code. But, you know, it would be nice if we had the current execution context handy in a variable and in a register. We already have registers, so let's just put it in a register. We can put it into R15. We have R10, 11, 12, and 15 available, looks like. So, registers. No. This is going to be running execution context base. That will be in 15. That's going to be cool, because that means that we'll have the result that this thing would give us anyway in a register, so we can just like index that far into it. But first things first, we gotta put it in that register. Compile. Let's see. So here is where we load up the register array, locals array. So why not also load up the execution context base here? It's going to be the execution what was it called? The running execution context base? It's a mouthful. arg3, will that make sense? What's going to be the argument number? Native executable run. Okay, so we run here. And this is the signature of our JIT generated JIT code. So it takes a VM, registers, locals, an entry point address. I think that is for generators, yielding. So I guess we'll be after that guy. So running. Oh, do I not have VM here? No, I do. I don't know. What am I doing? This is type def. Execution context. There we go. I'm going to pass in the running execution context and we'll have it. It's in 0, 1, 2, 3, 4, and arg4. Okay, arg4. Sure. Cool. So now that we have that, we also need to be able to have the offset of it. So it's offset 32 bytes into that struct. Well, let's just add an API, which is lexical environment offset non-standard layout type. Okay. I guess built-in offset isn't going to be any nicer to me, probably. I remember we had a trick for this in WebKit. It was something like offset of like class member, and then you would do like you would do like some pointer math, so like bit cast, like a putter diff t of that, and you have to subtract. But I think you can't. There was something about the null. You can't use null, so like you put some other value, and then something like this. Was this it? I wonder. I remember fidgeting with that math forever ago. Cannot take an address for a value of type. What the heck did they do? Oh. WebKit offset of. How did we do it in WebKit? Offset of. No, it was called something like object offset of. Okay. Yeah, this guy. Where are you from? Search for this symbol. Okay, I bet you it's in WTF stdlib extras. Offset of right. Okay. Yeah. I almost remembered what it looked like. All right, we're gonna take a look at this here. So casting the thing and then just subtracting, just doing the subtract. That's all I had to do. So it was fine the way it was, actually. Yeah. Okay. Kind of clunky looking, but let's put that in our stdlib extras. So you can see stdlib extras both in WebKit and in ACK. What are the chances? Okay, so assuming that thing works correctly, now we have the lexical environment offset thing. So we should be able to use that here. So the next step was just getting the VM lexical environment. Or we have the VM. No, we don't need the VM. What am I thinking about the VM? We have the lexical environment. So we just want to load that into something. So let's load it into GPR1. Let's say GPR1 is current lexical environment. Let's say operand GPR1, and then we are going to load. This is almost exactly what I want to do, but not from arg2, but rather running execution context base, and then the execution context lexical environment offset. There we go. Okay, so now we have the current environment in GPR1, and now we gotta jump this many hops. And hops is a member of cache. So we need to go to the cache value, read out the number of hops. Where is, what am I looking for? Environment coordinate. Hops is a U32. So again, we don't have a way to do a 32-bit read only, but we can do a little bit of, we can do one of them mask offs again, I guess. It's okay. And then we'll leave a fix me about just generating nicer instructions to read 32 bits only. I think that would be cool. Okay, so let's see. So now we need to do the jumps. So here comes, I guess that's that part. And then comes this part. Okay, so this part is going to be well, the hops, we can't just do this. So this is a little optimistic. We have to actually read from the cache in memory. And we have the cache at arg2, right? That's where the cache is. So we just want to read again here, but not loading the hash value, but rather loading the value. So the value offset. And then we also want to add on the offset of the field that we're trying to read here. So like hops offset and index offset. We need both of those guys. Okay. Bytecode. Wait, environment coordinate hops offset. Okay, so starting with GPR, 0 is hops. And then GPR1 is the environment. Right. So then we just need to like load GPR1 with its outer environment this many times. Okay, which means that we need a loop. So it occurs to me that I guess we could probably figure this out statically when we parse, actually. So like right now we do this at, we sort of cache on first access, but the parser could determine that like the number of hops that we would have to take here, so that it could be sort of part of the parsed program, the hop count. And the parser could also determine like the index of that thing in its environment. So if we had all that baked into the bytecode statically, we could even like not do a loop here, but we could unroll the loop. So you do like n number of pointer chases based on the hop count that we would know statically from parsing. But we can just do a loop for now. But it would be kind of cool to know it statically. Would be cool. Unrolling those guys. Anyways, future projects. But never having to hit the slow path would be good. That would be very cool. So let's see, what were we doing? We had the hops in GPR0, so now we need to make a loop. Right, so while GPR0 minus minus. Right, so we're gonna make a loop. I think we're gonna make a loop start and a loop end, actually. And here we want to check. Wait, don't I want to check here first if I need to stay in the loop? So massembler jump if GPR0 is equal to 0, then we need to jump to loop end. Exactly. Otherwise, this is start a loop right here. Wait, start of the loop should probably have the jump condition. Okay. It's a little bit of a strange way of programming, but you get kind of used to it, and it's fun in a way. So GPR1 is GPR1 outer environment. Right, that's exactly what we want to do. And then we need to teach him the offset of that thing. Also, we've been calling them outer environment offset. And you are in the environment. So let's see, environment just needs to have a way to access this guy right here. Static flat putter outer environment offset. You're reading my mind, dude. And we can't do that, but we can do that, I bet. Yes. Cool. Okay. Assembler jump loop start. Okay, so this is our end of the loop right here, which means that loop end links to right here. Which means that we can just do, yeah, something like that. It's pretty cute, actually. Maybe we should even do one of those so that labels don't escape this scope and confuse us. Okay. So am I doing this right? GPR0, that's our counter, our hop counter. We'll just decrement it. We need to also decrement it, I guess. I forgot to decrement. So let's see, assembler sub GPR0 1, and then we do that, and then we jump. Yeah, this could also be structured. I know that you could do a better instruction sequence, at least on x86, where you know, you could check the 0 flag after doing a decrement. So there's definitely a way to emit slightly nicer code, but we're not going to sweat that right very now. I think this should still be okay. Right, and then we have to check, now we are at the right environment. Now we have to check if it's permanently screwed by eval. If so, if it's not, well, if it is, then we have to go to slow case. So how do we get that flag? It's a Boolean right here. It's 9 bytes into it. It's going to be an unpleasant unaligned access right now with a mask. But we should definitely add that 8-bit access thingy. Permanently screwed by eval offset, right? Yeah, that'll be a very nice improvement to this, to add that, but let's not get distracted with that right now. So we're gonna load GPR 0, we don't need anymore because it was the hop counter, we're done with that, so we can load in as permanently screwed by eval from GPR 1, which is our environment pointer. GPR 1 now points to the environment holding our binding. Okay. Yeah, sure. Okay, so we have that, and then if that is, well, we need to mask it, right? Bitwise and do the dirty mask with FF. Sure. And then check for 0 or not. If it is screwed, then go to slow case. So if it's non-zero, not equal to 0, jump to slow case. Yes. Thank you, Copilot. You're so smart. Such a good boy. Fix me. Load 8 bits here directly instead of loading 64 and masking. Sure. Okay, so we made it past that check. Then we need to do this whole thing. Get binding value direct. Okay, so what does that do? It indexes into M bindings. Okay. So M bindings is a vector of bindings. And then we want to look at the initialized flag. And I don't want to do a throw in the fast path, obviously, so we'll just check. If it is uninitialized, we'll go to slow case. Let the slow case deal with all that. But we do need to get that flag out. Okay, and we also then need the value if it is initialized. So flat per value offset, I need a value, and I need the initialized offset. Thank you. And then it is a vector, so we do need to get the pointer inside of vector. There's no inline capacity here, so we know that the vector has an out-of-line heap allocated buffer, which is the outline buffer, as we call it. So we really just need a pointer to the outline buffer, and then we can index into that. Does that work? That might work. We'll find out. Okay, environment coordinate, blah, 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 declarative environment. Okay. You know, I'm going to start a compile here because it's probably going to take forever to rebuild with, you have to rebuild everything with all these new offset getters. It's not that bad, but just going to start one anyway so that we are a little bit more up to speed later. Okay, so I've loaded Right, so now I want to index into that array. So I want to say GPR 0 should become the environment M binding outline buffer cache index. Right, we have to get the cache index also. I guess, okay. We have the environment in GPR 1, so GPR 0 is free to do, wait, oh, hold on, did I say declarative environment? I need the offset of this guy also, M bindings, because you're at 24, and I don't know that. So static flat putter bindings offset. Sure. And that we're gonna get now. Ooh. Okay, wait, are we doing this right here? So GPR1, that's a declarative environment binding offset. Bindings, yeah, sorry. Plus the vector declarative environment binding outline buffer offset. There we go. There's that guy. Okay. So now we have a pointer to the outline buffer data. Then we just need to add to that pointer the index of the binding. So we need the index of the binding, which is stored in the cache. So here's where we load hops. Okay, so now we're gonna load the index. Maybe I need a third register here, actually. So I have the outline buffer. GPR. I feel like I need one more register. Or wait, I don't need GPR1. The environment had GPR. The environment was in GPR1, but I don't need that anymore. Once I have the outline buffer, I don't care about the environment anymore. I just don't care about the environment. The declarative environment, to be clear. I am Swedish. I do recycle, but that is not what we're here to talk about. So yeah, we'll allow ourselves to overwrite GPR1 here, which allows us to use GPR0 for the index, which we'll get from R2 value plus index offset. And then we need to mask that, right? Wait, I didn't mask hops. I need to mask the hops. So that's another ugly bitwise and. And actually, that's a bitwise and I can't do this because it will sign extend. Oh, that's kind of sad. Okay, you know what? This is the day when I added GPR2, which gets to be R12. Okay. So I can't do this because it will sign extend this guy. So I'm gonna have to load up GPR2 with this value right here. And I think we can actually keep that in GPR2 for the duration. can like keep it in there for the rest of this function. Hops. 32 bits directly. Yeah, this is really goofy, so we should be able to do a 32-bit mov here in this case, but I don't have that instruction right now, so we'll do an AND so we don't get totally confused. Yeah, we'll do that. Okay, and then next time we load from the index field, we do the same thing. Although at this point we know that GPR2 is already I'm just going to keep it there anyway since we aim to get rid of it. Yeah. Okay. Right, so now we have the index in GPR0, and we have the outline buffer in GPR1. So now we need to multiply the index by the size of a binding. So GPR0 size of declarative environment binding. So we need to do a mul. Do I have mul 32 at least? So it could overflow technically. We could probably use one of those effective address instructions here and let the CPU do the multiplication. Again, there's better ways to encode this. We're skipping past all the fanciness right now just to try to get to the point where we can test it and debug it. So I want to do mul 32 with an immediate. Multiply GPR0. Yeah, that seems good. Okay. So now I can load from GPR1 plus GPR0, and that's where we will find. Wait, if we just add them together, let's just add them together first of all. Add GPR1, GPR0. Okay, so now GPR1 is the address of the binding. And then we had to look at that field. What was it called? Initialized? Yeah, we have to check if binding is initialized. So we have to read another 8-bit read. Binding initialized. If it's not initialized, go to slow case. So let's see. Operand, we'll read the initialize into GPR0. That is exactly what I want to do, yes, exactly. Jump if, so if GPR0 is, actually I need to mask it once again because I don't have my fancy 8-bit mover. But here, I just want to jump to, if it's equal to 0, I gotta go to the slow case. All right. Now we're home free. So we need to get the binding value. So we should be able to get that from GPR1 plus the binding value offset. Wait, am I thinking about this right? Am I thinking about this right? I think so. Okay, so we load it into GPR0. That's our value. And then we store that into the accumulator. And then we bail. Jump end. And end is not a thing. Assembler. Label end. And the end is all the way down here. Okay. Well, that was a lot of code that we've just written. Let's see if if this works. get variable. Okay, we are failing somewhere. Verification failed, false, assembler.h. Okay, so we're trying to do something with the assembler that it doesn't know how to do. Line 561, verify not reached. We are in mole. Because we're trying to do a mole with an immediate, which I guess we don't support, but I want to support that. So I want to have like, type is operand, type immediate. Yes, please. Can I please have that? Come on, Copilot, you can do it. Are you thinking? Yeah, he's thinking. Okay, let's take a look here. If it fits in I8, then we can do one variant. Otherwise, we can do a 32-bit variant. 6B/5. I don't think this is right. Because imul has like, it's supposed to look like this. Like imul, like RAX, hex18 or whatever, or like 5, something like that. So this is the destination register, this is a source register, and this is an immediate. So in our case, because we're using an immediate as the source, it's a little bit weird. I guess we're not like allowing you to encode the full possibilities of the multiplication instruction here, but this is not right. It needs to be mod rm, I think, dest. Right, so we just emit the register twice. That's what we want here. Okay. Let's see. And did you just work? Okay. Did I just get it on the first try? Because that's pretty good. I want to look at the disassembly. Oh, what's going on here? Disassembly fails. Verification failed. Bytecode offset less than block size. I don't think that's my fault. What's going on? Maybe it's just an empty block and it doesn't know how to disassemble that. It's block 2. Block 2 is empty. I bet you that it just needs like a little bit of don't do that for empty blocks. 121 right here. How about if block size, yeah, something like that, I guess. I don't know. Does that seem fair? We can also just print nothing. Okay. So where's our get variable? Okay, this is our big chunky boy here. So this is all the code that we have just emitted. Goes here. The disassembly output is so nice, by the way. Shoutouts to Simon for implementing all that stuff. Simon has been doing really good stuff with the JIT. So now I feel almost guilty for doing all these goofy ands. But yeah, that's the code. So let's see. Okay, I gotta turn off disassembly. I was gonna say, like, let's see if it can run test.js. Test.js has no known failures at the moment, so we should see very quickly. I mean, other than some JIT instructions not being JITable yet. But if it has 0 errors, it doesn't have any errors. So it seems like maybe we just did it right. That's pretty cool if so. I'm sure this can be faster, definitely. But even so, like how fast are we now? So let's just get a ballpark number here. 500 milliseconds, 515 milliseconds, let's say. Although, okay, it varies, I guess, depending on what the computer is doing and so on. We got Clang indexing in C-line in the background. That tends to disturb performance numbers very heavily. But let's say 500 milliseconds, around that range, which is, if we go back to where we were before adding the fast path, how fast were we then? We were in the 1.3, 1.4 second range. So we've more than doubled the speed of our micro benchmark, which is fantastic. Okay. And all we had to do was some goofy stuff with, we had to like add some helpers here and there to get offset of fields and things. And it's a little bit of an intrusion because you are exposing that information, but at the same time, it's like, this is the same information the compiler has about, the C++ compiler has about our types. We're just making that information available at runtime to our JIT compiler, which seems reasonable. Let's see. I think that's probably okay. So I wonder how this affects the zlib test now. So of course, it will take 2.5 minutes to find out, but just as a quick test, like how fast would it run? Also, is the computer, yeah, the computer's doing a bunch of crap at the same time, so it's not really a fair test. I guess what would be more interesting is to find out if all the calls disappeared, or if many of the calls disappeared in call grind trace, which I would expect that they have. Yeah, so yeah, that assembly output is so far from optimal for that program. We can do so much better, but even so, it's still more than twice as fast, so it's great. Don't know how much faster it would be with less instructions. Probably faster. Less work is usually better. But I think maybe I'll just leave that as a fix me. And we should do some commits probably. So stdlib extras, let's do that one first. Add offset of macro that works on class member fields. Okay, and then expose offset of the has value and value of the optional internal fields. Yes. Expose the memory offset of vectors outline buffer pointer. All right. And then in the assembler, libjit x86-64 add. I guess we can say x86-64. Yeah, so we started moving a little bit towards supporting multiple architectures in the JIT assembler. So Nico has added the first abstraction layer, which is that now we have well, we have x86 assembler, and I think he wants to add an AR64 assembler, and then it's just typed deft. Like the one that's relevant for your platform is typed deft to assembler. But this allows us to have separate classes for the different architectural assemblers, which is good. By the way, let's just take a quick look here at where we ended up. So get variable, where are you? See, he's not even here. Get variable. Look at that thing. So it's gone from, what was it, like 14% in the first trace down to 0.3%. If essentially like getting rid of that thing entirely, which is fantastic because it was at 14%, even though most of it was cache hits. So we can do that fast path in machine code way, way, way faster than handling it in C++. Of course, I'm just thinking like there are some things that we don't do in the fast path. Like we don't have the verify assertions. We don't run those. Perhaps we should in the JIT code. I think it's probably okay not to. But something to consider. But let's not worry about that right now. It is really, really nice. And we can get even nicer if we simplify the instructions that we encode. Add mul32 with immediate. Allow mul32 with immediate operand. Yeah. And then this is just like exposing offsets of various things. Actually, you know what? Staged. I'm going to do the native executable thing where we added a register first. We added a register with the current execution context. So the running execution context base, I think that is something we can do separately here. Libjs JIT store the running execution context in a dedicated register. And then we had the dump thing. Libjs JIT don't crash when disassembling an empty basic block. Sure. We got all of these. Are they just offsets? Because if they're just offsets, they can probably be part of the change that we're doing here, the fast path. Okay, so let's clean that up. It's fine, fine, fine. Libjs JIT fast path for cached get variable accesses. Can now stay in machine code for environment variable accesses, read accesses, as long as they are cached and initialized. This is more than twice as fast. Micro benchmark. Oh, we don't need to say that, but I think I'm going to run zlib, the zlib test when I'm not recording, and then I'm gonna amend the commit with like what kind of improvement we're seeing. But I imagine it's going to be well, at least probably 10%, probably more. We'll see. We'll see. I'll put that into the thing. But it looks like a really helpful, optimization. So it's really, really cool. And yeah, obviously we have lots of other things to optimize. We got put by value, get by value. Those are harder because there are more things at play. And memory layout of objects is more complex than the environment. But there are some very common cases that we should fast path. I think right shift and left shift, super straightforward. If we can just melt those off here, that'd be great. We got unsigned right shift, a couple of percent. It's another good one to handle. Abstract equals, that's equal, not equal. So not the exact equal. I guess, yeah, we can do like this so we can see all the different C++ helpers that we're currently calling out to. Yeah, so a bunch of them, 1% or above, can probably add in 32 fast paths here for a bunch of things. Shave off a fair amount of execution time on the test. So more work to do. So it's a lot of fun stuff here. So we keep making the JIT better. That is very, very good. And yeah, I think this will be the end of today's video. So if you made it here, thank you so much for watching, for hanging out. I hope that you saw something interesting today. I think it's good to continue working on the JIT, making it go faster, and really starting to take advantage of the architecture that we have here, where it is a simple JIT, it is deterministic, but by emitting fast paths in the machine code, we can still get a lot of performance that we were unable to get before because we had to be more generic. And now we can stay out of C++, remain in the tight assembly code. That is really nice. And I'm curious to see, like, what are sort of where's the ceiling of performance that we can get with this architecture until we have to get fancier. But I know the ceiling, we're very far from the ceiling right now. That's a long way to go. So it's good to keep working on it. Anyways, it's the end of the video. If you made it here, I already said that. Thank you so much. And shout outs to everybody who's been helping out working on the JIT in the last couple of days. Really, really fun to see so many people come from the videos and join in the hacking. Just keep it coming, and I will see you all next time. Bye.